Hi, everyone. This is Stan Putzig, your Associate Director, stepping in for Amanda Hendricks, who's on vacation this week. It's my pleasure to introduce Keith Noll. He's a planetary astronomer at the Goddard Space Flight Center, and he serves as the project scientist for the Lucy NASA Discovery mission. Today, he's going to be presenting results from Lucy's passage of some main belt asteroids on its way to the Jupiter Trojans. Go ahead and take it away, Keith.
All right, great. Thanks. Well, thank you guys for having me here. It's a pleasure to give this presentation. I know many of the people, I hope, that are online. I can't actually see, but I know many of the people at PSI. So here's my quick overview of the talk. I'll give a super short introduction to the mission, since I think most of you probably know about it by now. Then I'll talk about the flyby of Dinkinesh and Salam. That was our first main belt flyby. Then the more recent flyby of Donaldjohanson. And in both cases, I'm just going to touch on sort of the top level results. There's a lot of more details that will be worked out over the coming years, I'm sure. Next to last, I'll talk about Trojan binaries and bilobes. That's a particular interest of mine. And then finally, just an idea of where we're going next with all this. Okay, so what's the Lucy mission? It's a discovery mission, as was mentioned. It's got PI, that's Hal Levison, who I think most of you know. There's a photo of our science team at the launch. And I'm sure, again, as you all know, any kind of a mission is not the effort of a single or even a small group of people. It's an effort of hundreds. So a lot of what I'm going to present today is work that other people have taken the lead on, but it's sort of altogether what the Lucy mission is doing. Lucy is not an acronym. It was named after the Lucy fossil, and the idea here is the main driver of the mission is to test the idea that the Trojans were captured objects that were formed in the outer protoplanetary disk, and then are the lucky few survivors that are captured in the Trojans at the end of the giant planet migration. And that requires a tour. You couldn't just go to one because it's not going to be made in the outer protoplanetary disk label on any of these things. So we're going to rely on comparing and contrasting various features that we can see. And in advance, we don't necessarily know what the key observations are going to be. So we want to have a broad mission that does more or less everything you can do. These are flybys. So it's a typical flyby mission. And there's some recent summaries in space science reviews that you can look at, or there's some older papers in PSJ from 2021 that give good summaries of the mission. This is our famous pretzel diagram. It's a non-inertial frame, so obviously we're not making maneuvers that look like that, but it's a good summary all in one chart of the various waystones all along the way on our mission. So we're going to just go up through the L4 in this talk, and the L5 is the last piece of the mission that happens in 2033, and I'll leave that for a future talk. Here's what we're carrying on board Lucy. The instrument platform's up at the top. It's pointable. We have instruments that have been inherited from previous missions that have heritage. So there's a LORRI camera. That's our workhorse high resolution camera. We have LTES, that's a thermal emission spectrometer. LRALPH is two instruments in one, really, a visible imaging camera with color filters, and then infrared imaging spectrograph with a linear etalon, that's LISA. And that's what we're going to use for our compositional information. We're also going to use two spacecraft systems to do science. TTCam is our tracking camera. It's a wide field camera, but at closest approach, it's a great camera for getting context and doing some good science. And then we will use Doppler tracking of our radio signal to determine masses. Okay, so that's the super quick summary. I feel free to ask questions at the end if I've left something out, or maybe you had a burning question. But I want to move on to Dinkinesh. So Dinkinesh was not part of our original mission, but one thing that we did have was the idea that we were going to use terminal tracking. And this figure on the lower right, I don't know if you can see my cursor, shows the idea that instead of just blindly pointing as you do the flyby and taking mostly images of empty sky, if you have active tracking on board and ranging, you can keep the instruments pointed at your target as you do the flyby. So that's a fairly novel system, and it was maybe one of the least tested pieces of our spacecraft. So we wanted to test it, and Donaldjohanson, the small body I'll talk about next, was the test case, but it wasn't an especially good one for various reasons. And Raphael Marchal independently was looking for close approach opportunities, just sort of as an aside, were we going past anything? And he was looking at much smaller objects than we had looked at previously, down to sub-kilometer. And he found one that we were passing within 16 meters per second delta V. So super close, super easy to get to. And in January of 23, we made the decision to go for it. This is with like less than 10 months of advance warning. So that was really late in the game, and Lockheed Martin and all our operational team did a fantastic job of working up to being able to do this, especially since we were coming off dealing with our solar panels and other operational issues. But we did it. And here's just an illustration of why this was a very good encounter to test the terminal tracking, because the geometry of the encounter is very similar to the encounters that we'll have at the Trojans, which are more or less at 90 degrees. So we throw the spacecraft out in front of the target and it overtakes us, and we have roughly 90 degree, plus or minus 20 or 30 degree encounters for the approach and departure angles. So we didn't know very much about this, except that it was a smallish asteroid in the inner main belt. And we were still worried about the size of this thing, because we thought that if it was too small and maybe below 500 meters in diameter, the terminal tracking might not work. So we went ahead and some of our collaborators got spectra at ground-based observatories based on the spectral type and typical albedos that we would expect. We figured, okay, it's probably doable. And it turned out to be pretty close guesses. So this is all nice ground truth that you can use to sort of validate other observations of objects where you don't have a flyby. So here's our first, well, yeah, so we were expecting a very ordinary asteroid, and none of us were too excited about it, except that, you know, we would get a good chance to do an engineering test. Here is one of the best photos. This is not staged. Stuart Robbins took this photo, and this is the first look at what we saw at Dinkinesh. And as you can see, it was anything but ordinary. Here's the flyby. This is about 20 minutes of imaging compressed into the sequence. And you can see that we're just flying by, and the tracking worked flawlessly. So we were super happy about that. In fact, this was a much harder test than we would have expected, because the way the terminal tracking is designed to work, it takes into account that there could be more than one object in the field. So it found two objects, and then as we swing around, it says, oh, no, there's only one. And then it said, oh, there's two again, but it stayed pointed on the brightest target, and it was an unexpectedly rigorous test, but it was fantastic. So what did we see? Well, this is On the right, you see Dinkinesh itself, and then you see Salam, the satellite, in the background. This was more or less our first view of this of the satellite. We had to wait a day or two before we could see all of these on the left, where you see Salam itself now centered in this frame and changing aspects as we do the flyby. And you can see that it's quite a remarkable object. We've named features on Dinkinesh and Salam. These are sort of the main primary features of interest. So there's ridges, there's an equatorial ridge, there are troughs, there are other features, boulders, and the two lobes of the satellite all are of interest in trying to figure out, what is the history of this object? How did it end up like this? You can also do a comparison with a very interesting comparison with Didymos. So these are both S-type asteroids. They're the first two binary asteroids that we've seen close up, almost at the same time, in fact. But you notice some differences. The Didymos system is much more compact, and the satellite of Didymos, Dimorphos, is very, very different than Salam. Dimorphos looks like a fully relaxed rubble pile, whereas Salam has structure and clearly is not fully relaxed in terms of just a hydrostatic shape. Both Didymos and Dinkinesh have notable structures, angular structures, troughs, ridges, and so on. So there's some interesting questions here about strengths of materials and what determines what these objects eventually end up looking like. And I think that's an area for future research that will be investigated. But we wanted to try to understand what happened to get us to where we see Dinkinesh today. And because this is a small asteroid, anything less than about 10 kilometers in the main belt, and near-Earth populations are heavily influenced by Europe, which, as you can see with this inset figure, a lot of the objects that we know about are spinning near the breakup speed. And Dinkinesh was probably spun up to this breakup speed as well. And you can see this suggestion in this little animation on the right here of what might have happened. It looks like this feature that is highlighted in cyan was actually pulled away, originally connected to a more symmetric body, and pulled away with some kind of structural failure, probably along a pre-existing fault, that would have led to mass shedding and triggered the whole satellite formation, the formation of the equatorial ridge, and so on. We don't know for sure, but this is sort of a working hypothesis about how Salam formed. And we know that in general, this is a pretty common process. We see satellites around these fast rotating bodies. We see asteroid pairs, which are previous satellites that have now gone off on their own. So we know that this is a common process in the near-Earth populations and the main belt. So it's great to get to see one up close. And the other thing that's novel here is that Dinkinesh is by far the smallest main belt body we've seen, and it's on the same scale as the near-Earth asteroids that we see. So it provides a bridge where you can get rid of questions about, well, how much does the size matter? So it's been a great value in that sense. One of the other things we had to figure out was the spin state of this body. Coming in, we were confused with the light curve photometry that we were taking, it was sort of bouncing around and we didn't understand exactly what we were going to see. Because it was a fairly high amplitude and long period, we thought maybe we'd just see a single extended object that was a slow rotator with a period of about 52 hours. Once we saw the satellite, we knew that something more complicated was going on. And because of the separation of the orbit, it's likely that Salam would be tidally synchronous, and it turns out that it is. We didn't know about the spin of the primary. John Spencer was able to determine that by feature tracking. So we were able to tease apart, and the result is that you've got a fairly rapidly spinning primary with a synchronous secondary on a 52-hour orbit. And both are retrograde. We can determine that from the light curve itself. And in fact, if you look at this figure down here, you can see that there are mutual events that are shadowing events with the little sun symbol labeled C and G. And this is 96 hours of photometry taken on the egress, looking back as we went past. And so almost 2 full periods of Salam's orbit. And you can see that when you get, oops, what did I do? When you get to these points, you see that the shadow of one of the bodies that's on the other is seen from the sun, and that we can see that in the light curve. The other thing that's pretty surprising about this that really puzzled us for a while is that we didn't expect that the satellite would dominate the light curve, but in fact it does. And that's just because it's such an extended object. So with a more than 2-to-1 aspect ratio and a relatively large size compared to the primary, and the primary itself being relatively uniform, most of the light curve amplitude that we can see, both from the ground and from Lucy, was Salam itself. So that was kind of a fun puzzle to pull together. So what do we think is going on here? Well, we have sort of 3 different basic cartoon scenarios. The first 2 steps in both are the same, that you get Yorp spin up and then you get some kind of mass shedding event that forms a ring. And probably the simplest one is the first, where we just immediately get the 2 satellites forming and eventually merging into the contact binary, and the remaining material that's in the ring falls back on the surface and forms the equatorial ridge. There's 2 variants of that you could imagine. So one is that you have 2 different mass shedding events with 1 satellite formed in each, and that later merge into the contact binary. The question there is, how likely do you think it might be that you would get the same size satellite formed in each of these events? Now, it may be that when you do these mass shedding events, they tend to be roughly the same order of magnitude, and this is just a coincidence. But it's hard to know how much weight to put on that scenario. The other possibility is that you get a single satellite forming, but it is also spinning rapidly, and that gets torqued on a pretty short time scale by spin orbit coupling or Yorp, that then later fissions to form a contact binary. Again, I'm not sure we can rule this out, but it is a more complicated scenario than the first one. So I think people will have a lot of fun playing with these and sort of trying to figure out which is the most likely scenario for forming this contact binary satellite. All right, here's the big takeaways from Dinkinesh. Shape and spin state strongly suggest the Yorp spin up and structural failure, resulting in mass shedding and satellite formation. I didn't talk about craters, but the surface age for the craters on Dinkinesh is about 10 million years. And that's much shorter than its collisional lifetime in the inner main belt. So it has been resurfaced since it was last disrupted, probably, which is consistent with a mass shedding event. There's only a few craters seen on Salam, so it's potentially much younger. And it could be that these things just repeatedly have these Yorp spin up and mass shedding events, satellite formation, eventual loss of the satellite, and the whole scenario repeats. there's many similarities to the NEA binaries that we see many more of. So this is the first opportunity to see this in the main belt, where you can now compare and contrast different environmental factors and roll out things like tidal interactions with Earth or other planets as the main driver, since we see the same thing happening in an ordinary main belt asteroid. And finally, the lesson learned is just that even these tiny, ordinary, run-of-the-mill main belt asteroids could be very complex, and that York may be a fairly rich source of variety in small asteroids. Okay, let's talk about Donaldjohanson. What did we know about it before the encounter? Well, we knew that it was, based on its orbit, it was a likely member of the Aragoni family, although you can't rule out an interloper. Most of the Aragoni families are C types, and I think before the encounter, we knew that DJ was probably a C type as well. The impact itself was probably a cratering event or just subcatastrophic. DJ was a slow rotator with a large amplitude, almost more than 1.5 magnitude. So we expected a highly elongated object or a binary. And the WISE diameter, effective diameter, is 4.3 kilometers, but that was pretty uncertain because of the long light curve period. So we didn't know which phase that measurement was obtained at. Here's what we were guessing, and here's the flyby video, and we were kind of right. So this one was less of a surprise than Dinky. We more or less were able to figure out from ground-based data what we would see, and probably the main surprise is that it's larger than we thought. So the overall dimensions are about almost 9 kilometers long by 4 kilometers at the widest. But again, that's consistent with WISE thermal imaging being taken at an unknown phase. So it could have been looking at it end on, when that would have been more or less right. So there's a few things that I want you to notice as you're looking at this video, especially in the neck region, which joins the two lobes. I want you to see how different the topography there looks than on the lobes themselves. And there's lighting issues to consider. We're at low phase here, but it is a distinct region on this body. So that's sort of one of the main mysteries that we tried to figure out in our first papers here. And some of this stuff's been presented at DPS, and we have a paper in press in Science that will cover most of what I'm going to show next. So again, we've named sort of the major features on this thing, including the two lobes and the neck region, a couple of regions that seem to be more smooth on either side, and this ridge that bifurcates the neck. So all sort of interesting stuff. There's some weird boulders, very elongated columnar boulders. Here's a view of the gravity, a gravity map. And what you can see is that, or a slope map, I'm sorry, this is slope. What you can see is that the slope is very smooth in the neck region, and it is all pointing downhill, so from left to right until you get to the ridge, and then the slope is pointing slightly in the other direction. So stuff is flowing from the small lobe down the neck, and that probably is the explanation for what's going on in terms of the smoothness of the neck, and also the fact that the craters on the neck are somewhat less distinct. So probably some of them are getting partially filled. Although the crater counts look about the same on the neck as on the two lobes. If this thing were spinning faster, so it was originally probably spinning much faster than 250 hours, it was probably spinning at sort of 5 hours or less, which are breakups for these types of objects, the direction of the flow would have been opposite. So in other words, when this thing formed, it was probably material migrating from the narrow part of the neck outward to the lobes. And then as it slowed down through Yorp, that direction changed. The tip over point is somewhere around 10 hours rotation. And at the current very slow rotation rate, that is distinctly downhill. Another interesting feature of DJ is that it has also a sort of initially confusing light curve. So we were getting fairly sparse measurements on the inbound leg from Lucy. We had also extensive ground-based light curve data, and we knew roughly what the overall period was, but there were residuals that were larger than we would have expected. And the answer turns out to be that there's a likely non-principal axis rotation. So a two-period Fourier fits better. And you can see from the gray residuals versus the black point residuals on the lower plot. Tom Statler has actually put together a toy model of a non-principal axis rotator that does an even better job of fitting these data. And what you can't see here is that when you get to this more dense time sequence here, right before closest approach, there's a very distinct flat bottom to this light curve that is a telltale giveaway of a binary or a bilobed object. So we kind of knew at least a half a day before from observations themselves what we were likely going to see. But this has also been sort of a fun toy problem. And it's likely that many slow rotators, so the Yorp can either speed you up or spin you down. And for those that spin down, they eventually are likely to enter this non-principal axis rotation state. Another famous one that's in that kind of state is Tutatis. We got spectra, and this was with this is a combination. The black points are a combination of LRALPH and MVIC, and compared to IRTF data in blue and a Frankenstein montage of spectra from Aragoni family members and Aragoni itself in red. But what you can see is that it all looks pretty consistent. This does look like you would expect an Aragoni family member to look like. The uncertainties on our LRALPH data are high because this is at a temperature regime that it's not designed to work in. So we're just being very conservative. But I think you can see that internally, it looks like it's probably much better than our conservative error estimates. And you see this very strong 2.8 micron feature. And so that's pretty cool. We're glad to know that Lisa and LRALPH are working in great state, even when they're not in their optimal conditions. And we're expecting really good results when we get to the Trojans. And meanwhile, for DJ itself, it looks like it is as you would expect an Aragoni family member to look. It looks very similar to CM chondrites. It looks a little bit like Bennu. Bennu's got a weaker feature, but overall, it looks like it's consistent with being a member of the Aragoni family. Or here's a crater counts, and the red is on the small lobe. The orange points are on the large lobe. The diagonal line is the theoretical saturation for craters. The tan points are Bennu crater counts, and the gray points are Matilda. So we're just comparing different objects here. And you can see that for craters larger than about 400 meters, Donaldjohanson also is approaching or at this theoretical uh, saturation limit. And from that and estimates of the material strength, you can get a surface age that is consistent with the 150 million to 200 million year age of the Aragoni family itself. So that's the sort of big, high level conclusion that I want to highlight today. There's a lot more going on in this figure. You can see that there's a crater deficit once you get to smaller sizes. That suggests some kind of crater erasure event, maybe 20 to 40 million years ago. That's going to take more work to get into, and I'm not going to try to get into that here today. But in terms of the big picture, it looks like Donaldjohanson is probably more or less as it was formed by the Aragoni family forming event, without a lot of major changes since that time. So that brings us to, there's a large collection of bilobed objects out there, and they all have this surprisingly similar structure. In fact, when we put Donaldjohanson and Tucson next to one another, they're almost like twins, except for slightly different sizes. So that led us to ask the question of, well, how come they all look like this? And there's a couple of boundaries you can put on this. If you have lots of pieces that you're putting together to form a bilobed object, you would expect the lobes to be very similar in size. So you can run simulations and find that if you want to get a mean size in the 0.7 for the lobe effective radius ratio to be, in that range, you need a small number of fragments, and just randomly picking which lobe to add the fragments to, you end up with unequal size lobes. This doesn't look especially like the satellites that we see for, or the majority of the satellites. They're smaller, and those are probably the satellites that are formed from this spin up and mass loss, mass shedding, like a Dinkinesh. And Dinkinesh would be in this lower group down here, this type A. There's a few objects up here in this larger size ratio, but not as many. So I think there's some interesting things to do here. First of which is to get more data. And Richard Cannon is a postdoc or grad student working on this problem. He's doing some interesting work. And then I think there's dynamical work too to understand exactly how you get not just the mean relative sizes, but the size distributions that we see. Okay, so here's the summary for DJ. Looks like a C-type object. Surface age is consistent with the age of the family. You can get the spin state that we see in less than 100 million years, so that's nothing weird about that. It's prograde. That's consistent with the Yarkovsky migration outward from the center of the family. The bilobe itself probably is the result of forming directly after the collision, and it appears to be a typical Aragoni family member. In some ways, studying these typical objects is good because it gives us ground truth. And when you look at other similar objects, you can be fairly confident that you understand what's going on from your ground-based observations only, since we got it pretty close to right for Donaldjohanson itself. All right, I'm getting a little short on time, so I'm going to go through this kind of fast. As I said, I'm interested in binaries, and if you sort of reframe the Lucy mission, it's a binaries mission. All of our targets, except for Orus so far, are known to either have satellites or be a bilobed object, or a likely bilobed object. So that's kind of fun. And here's how these have been identified. There's a real deficit of known binaries in the Trojans, just because it's in this uncomfortable middle range where it's far enough and faint enough that it's hard to get them from the ground. There are no wide binaries like there are in the Kuiper belt. So we don't have a large inventory of known And the Trojans are generally smaller than the Kuiper Belt objects. So we don't have a large inventory, but this is what we could do with Hubble. That's how we found the satellite of Euripides. And we can put good limits on small satellites that are far from our targets. What we cannot do from the ground or from Hubble is look close in. And the blue circles, the inner blue circles, show where both Hubble sensitivity starts to decrease pretty drastically. And that's also where most known satellites are. So I think there's still, even though we don't see them with Hubble, there's still good chances that we will find some with Lucy. We want to know the orbits, and especially because they help us determine the mass. And Palomelli is a special case because it's the smallest Trojan. So it's the one where we can get the least accurate mass determination from Lucy Doppler tracking itself. But it has a satellite that we found. It was found by stellar occultation, which is unusual. We know the rough size, and with some assumptions, we can make some constraints on the orbit. So if we assume that it's the spin axis or if we think we know the spin axis from light curves, if we assume that the eccentricity is close to 0, which might be a dicey assumption, but it seems to be plausible, and we just assume that it has a reasonable density, you can get a period constrained to be within 14 to 16 days. What we'd really like to do is be able to have targeted observations with Lucy during the flyby. To do that, we are going to need a much better determination of the orbit. We'll start detecting the satellite properly about 20 days out. And at about 5 days out, if we have an orbit determined, we'll be able to upload a secondary ephemeris and point at the satellite and get high resolution imaging. We have an idea to try one more long shot chance to constrain it from the ground before we get there. So stay tuned. We hope that we're going to be able to do this. All right. The Trojan population itself, though, is pretty small, but there's a bunch of outer main belt C-type large asteroids that have satellites. So if you plot those up along with the Trojans, you get enough that you can start to look at trends. And you can see that there's a couple of types. There's the equal mass binaries, there's the wide binaries, there's only 3 of those, and then there's the normal ones. And you can see that we have one in each of these groups. So we have Patroclus up in the equal mass, we have Euripides with its very wide satellite Keta, and then we have shown by the red cross, Palomelli, with its satellite where it's not as well determined, but it looks more or less like a normal satellite. One of the things that you notice if you look at the outer main belt satellites is that there are satellite systems. So there's quite a few where there's 2 or 3 satellites, and those also seem to follow trends. So just based on purely empirical extrapolation, if you were to look at Euripides and say, well, if it were to have additional satellites, where might they be? You could see that there's plenty of room where you could hide them. You wouldn't be able to see them with Hubble, and they would not at all be surprising. In fact, because Euripides is the parent body of a collisional family, the largest collisional family we know of in the Trojans, we kind of expect that its satellites will have formed post-collision. And when we look at other systems like that, for example, the Pluto system, we tend to see multiple systems with near resonant orbits. And I've got a case of beer, I think, bet on that we're going to find more of these. So we'll see. There's certainly room for a second small satellite for Palomelli as well. We don't know. And, even Lucas or Orus that don't have any known satellites now could easily have closer in satellites in this sort of normal range. So I think there's a lot of potential here for surprises, and let's hope to be surprised. All right, here's the conclusions for the binaries. So we're going to get a lot of binary data. We've already started with Hubble, but there's more to do. We're going to use the binary orbits for mass determinations. We've already got good system masses for Euripides and Patroclus. We hope we'll get that for Palomelli from the satellite orbit too. And the reason we're doing that is to get densities. And the key measurement for all of these bodies is not so much the mass, but the volume. The volume is the limiting factor for determining densities. And we do that with their imaging. And finally, I will be surprised if we don't find more satellites with Lucy. All right, what's next? So we have our next encounter with Euripides on August 12th, 2027. That's only less than 2 years away, which is scary. Our last encounter in the L4 is November 11th, 2028, so 3 years from yesterday. In that 15 months, we're going to fly by a total of at least 8 Trojan objects in these 4 systems, and probably more because there's probably undiscovered satellites. And it's going to be pretty crazy. Then we get a rest for a few years, and then finally we end the mission in 2033 with the Patroclus Menetius flyby. I know someone will ask, so I'll just say we have enough. If we have enough fuel, there's certainly possibility of an extended mission, but that's going to have to wait for some time in the future. All right, so overall, our working hypothesis for the Lucy mission is that the Trojans were formed in the outer protoplanetary disk, were captured at the end of giant planet migration. How are we going to test that? Well, we're going to ask questions like, how are the Trojans related to other solar system populations? We'll do that with one of the most interesting ways, I think, is density determinations. It looks like already, if you look at the densities we've got for Euripides and Patroclus, even before we get much better volume estimates, they are much closer to the densities of TNOs than they are to C-type objects in the outer main belt. So they're lower density than the outer main belt C-types. That would be interesting because it would suggest more volatiles are retained, which would sort of fit with the idea that you migrate things in, they lose volatiles, they get thicker regoliths, but once you get that insulating regolith, you can retain the stuff below, and maybe that is a history that makes sense. Another important question is, what are the role of impacts in determining not just the colors of Trojans and related bodies, but also their structure, satellite systems, and so on. The key pair here is Euripides and Orus, which are almost the same size. They're in very similar orbits. We know that Euripides has had a major collision. There's no evidence that Orus has. Orus is a D-type, so very red. Euripides is an unusual C-type in the Trojans. So it's sort of a perfect test of, what do we see when we look at these two similar but different objects? Are we going to see evidence of distinct composition, maybe in the base of young craters, or are we going to find other evidence of different regolith depths, subsurface volatiles? So I think this is all to be done. With JWST spectra, we already have seen that the spectra of Euripides and Orus show different CO2 bands. Unfortunately, we won't see those with the Lucy, but there are also features in the 3.3 to 3.6 micron range, and 2.8 micron bands, phyllosilicated bands, where we'll be able to look for global and local variability. What can we say about if these bodies are more or less primordial, or have they been heavily evolved by collisions or other things? With near equal mass binaries, at least in the Kuiper belt, we think that those are more or less primordial bodies. But when we get down to smaller bodies, are there other kinds of evidence? So, for example, if we find that Polymelli looks like a very regular oblate ellipsoid, that might be an argument in favor of it being relatively primordial. Are there any other identifiable characteristics with size or other properties? I think we're going to have to wait to see. Finally, what do satellites tell us about collisional processes? They're common, small satellites at least, are common products of large collisions. We think that Euripides will have, we know it has one, we think it might have others. Do we see these only at Euripides, or do we see them around other around other Trojan targets? I think these are open and interesting questions. All right, I think I am going to end there, and we have much more to come, but I'm happy to take some questions.
Thank you, Keith. That was a fascinating presentation.
Thanks.
So, folks, if you have a question, go ahead and speak up. And don't forget to unmute. So I'll throw a question out there to get us started. At one point you were discussing the DJ neck, and you said that the cratering counts were similar on the neck as the other areas.
Yes.
But you suggested also that there was some material that was sort of sloughing off, I think, of the smaller lobe into the neck.
Right.
Finally, do you have enough information to know whether the craters are shallower in the neck than on the lobes?
We don't have good depth measurements yet. Partly that's because the DJ flyby was at low phase, so we don't have as good information about topography as we might otherwise have wanted to have. What we do see is that if we make a distinction between what we call high confidence craters and probable craters, there are fewer high confidence craters on the neck. So that would suggest just the scenario that you're describing, that you get some partial fill-in of the craters, especially the smaller ones, on the neck region, but you can still make them out. So they're not completely buried, but if you count all the craters, the SFTs look almost identical in the neck and the lobes, which is surprising. When you look at it visually, it looks like there's many more craters on the lobes. So this is just, from careful work by our crater counters.
Okay, thanks.
Yeah.
Other questions?
This is Carly. I could ask Keith to expand on something. And I feel a bit cheaty because I'm on Lucy too, but
yeah.
I didn't know if Keith wanted to expand on the problem with the solar panels and whether it has any impact on either the upcoming the upcoming encounters or the possibility for an extended mission.
Carly, you're going to cause me to have nightmares now. I've spent the last couple of years trying to forget about that.
I'm sorry, I should have put a trigger warning on the question.
Yes, trigger warning. So this photo you're looking at was taken right after launch, and by the time I drove from where this picture was taken back to the space where we were getting communications from the spacecraft, we had already figured out that there was something wrong. So the elation after the launch was very short-lived. We saw temperatures that didn't make sense. The motor that was used to deploy the solar arrays had stopped. So there was some thought that that meant that they had deployed, but it turned out that one of the two large solar arrays had not deployed all the way. Luckily, we were getting enough power that we were not in any danger of not surviving, so we were okay. And then we spent the next year and a half running tests in the lab and trying to figure out every scenario of what could go wrong. It turns out that the lanyard, and when I say lanyard, it's about the kind of thing that you would have around your neck at a conference, except it's made Kevlar, luckily, that it had wound over the edge of the reel during the deployment and gotten wedged in between. There was a backup motor on the deployment motor, so we were able to use both motors to essentially double the torque. And that got us from about 75% open to about 98% open. At that point, we weren't worried about power, but we were worried about structural stability because like your umbrella, if your umbrella is 98% open, it's still pretty floppy. But once it's all the way open and latched, then it's stable. And that's what we were counting on. We were especially worried that during main engine firings that if the solar array were too floppy, you could break connections that cross the panel boundaries. Luckily, that all worked. So after tons of modeling and worrying and various attempts to open the array, we're now in a situation where we think it's pretty stable. We still have the largest impulse main engine event coming up after the L4. And it's mainly the largest because our mass will be much lower by then. We'll have burned off more than half of our fuel. But it's not going to be that much higher than what we've already experienced. So we think we're good. Fingers crossed and knocking on wood.
Sorry for making you relive that. Thanks, Keith.
Yeah.
All right. Other questions? So, Keith, am I getting the wrong impression that non-binary singular objects are rare?
It seems like that might be true, right? It's really, who would have thought that something as small as, a 700-meter main belt asteroid would have a satellite, and as something as complex as Salam. In a way, it's mind-boggling. I mean, physics-wise, yeah, sure, it makes sense, right? But it's been a surprise to me.
So in the last few minutes, we're going to. This is Carly again. If someone has a question, sorry, that isn't me, then please do speak up. Sorry.
Go ahead.
Okay, sorry. Keith, I wondered if you could. So we're going to, once we get to these bigger targets, we're going to be able to start really resolving composition on the surface.
Yes.
So I was going to get you to speculate what we might discover, which is just a really horrible question. Especially
what we want to discover is what we said we wanted to discover was compositional variations, right? And especially if we can tie those to ages of things. So, for example, if you saw what looks like a fresh crater from morphology, and it had an interior depth that was below what you think the regolith is, and it looks different composition, or maybe there's compositional layering on the walls of the crater. That's the kind of thing I think we're really especially interested in, because the kinds of questions you want to answer with that is, how thick is the regolith? We think there's ice. There has to be ice, but it's buried. How deep is it buried? Does it vary with latitude and solar insolation? Can that help us sort of piece together what the dynamical history of these things might have been in transit. Did they ever get much closer than 5 AU where they are now? So I think those are the kinds of questions we want to answer with the resolved spectroscopy that we're going to be able to do.
Awesome.
Looks like Henry has a question. Henry?
Hi, yeah. Thanks, Keith, for the talk. Sorry, I came
Henry.
late because I was coming from another meeting. I think I heard you say that the binaries are collisionally formed, and so I was wondering, is there any reason to expect triple or higher, more satellite systems?
Yeah.
And if not, like, why have you only seen binaries so far? Or if so, what yeah. I think you know what I'm asking.
Yeah, so I think, if you look at the outer main belt, you see triples, and there's even one with 3 satellites. So I would be surprised. And actually, the other interesting thing is, besides those all being C-type bodies, they're also collisional family parents, typically. So at least with Euripides, I would be very surprised if there weren't more satellites. And there could be, it could be a triple or quadruple. I think that seems to be a pretty common mode. And Pluto, for example, right? It's got a lot of small satellites. One thing, when you get up to the more equal mass binaries, so Patroclus for sure, and maybe for Polymele, those may not be collisional. Those may be primordial. In the Kuiper belt, we think they are for sure the equal mass binaries. So that's another point of connection. If you can convince yourself that these look like primordial systems, that is another tie back to the outer protoplanetary disk.
Yeah, thanks.
Yep.
Okay, any other questions out there? All right, well, as we've reached the top of the hour, I'd like to thank Keith again for this fascinating presentation. And we look forward to interacting with you more in the future.
Me too. Oh, I see Susan's on there. Yeah, thanks, Susan.